So in this session we're gonna uh, move to chapter 5. We'll start with constant variables. So in Java we often use the keyword final to declare a constant. So a constant is just a variable whose value doesn't change after you set it once. So the idea is, if it's marked final, the compiler won't let you accidentally change it later. So by convention, constants are all written in all caps with underscores. For example, if we want to keep track of sales tax rate, instead of saying 0.0825 like all over the place, we write it something like this. Let me do that. So final, so constant double tax rate is equal to 0.08 let's say 25. So now whenever we need to calculate tax, we just use rate tax. It makes the code easier to read. Someone can glance at it and know exactly what the number is for. And if the tax rate ever changes, you only update it in one place instead of hunting down every 0.0825 in your code. So some of the things to remember is forgetting the final keyword. So without it, the compiler lets you reassign the variable, which defeats the whole point. And mixing magic numbers in your code instead of replacing them with constants. So if you see numbers that look random like 7.3 or 42, ask yourself, should this be a named constant instead? So which do you think is clear, using 0.025 all over your program, or writing tax rate once and reusing it, and why? So the obvious answer is tax rate only makes the code cleaner, but it also not only makes the code cleaner but also makes future changes way less painful. Yeah, that's about the constants. And next is math methods. So let's talk some of the built-in math tools that Java gives us. These live in the math class and they are ready for you to use with no extra setup needed. So here are some common ones. Most common ones, we have ABS, which is absolute value. ABS -1 gives 1, and we have POW, which is exponent. So POW 2, 3 gives you 8. We have square root. Square root 9 gives us 3. Minimum, maximum, pick the smaller or larger of two values. We have round, floor, ceil, which are different ways to deal with decimals. Round gives you nearest whole number. Floor always goes down. Ceil always goes up. So example is, imagine a game score system. If a player loses health, you use ABS to make sure you only care about the magnitude of the drop. Or if you're simulating physics, you might need POW, exponent, for squaring a velocity, or square root for distance calculations. Again, some of the things to remember is so some folks try to use this for exponents because that's how it looks in math, but in Java this is a bitwise operator, not exponentiation. If you want powers, always use math.pow. Another thing is round just rounds a number to the nearest whole number. It doesn't format it to do two decimal places. If you want formatting for output, that's a different tool, which is a printf for decimal format. So if I ask which method gives the larger of two values, it is math.max, and its partner math.min gives you the smaller. So the math class is your toolbox for common operations. Whenever you are attempting to reinvent the wheel, like writing your own square root function, check if it's already there. Most of the time it is. So yeah. Next is integer division and modulo. So let's first, the rule: when you divide an integer by an integer in Java, the result is an integer. So Java truncates the decimal part. It doesn't round. It just chops off everything after the decimal. Like for example, 5 by 2 gives you 2, not 2.5. So if you want a decimal, make it at least one side a decimal, which is it could be 5 divided by 2.0 gives you 2.5. So this matters anytime you think you're calculating an average or speed or anything that should have decimals. If both operands are int, you'll lose the fractional part. And we have modulo. Modulo gives you the remainder after division, 7 modulo 3 is 1, because 7 is equal to 2 multiplied by 3 plus 1, so remainder is 1. And 10 modulo 2 is 0, which is no remainder. So think of modulo as a great tool for patterns, even on odd checks, or every nth time, or cycling through a small set of states. Practical uses are even, odd, like n modulo 2 equals 0 means even. If n modulo 2 not equal to 0, that means odd. For every nth action, you tick modulo 5 equals 0 means do something every nth tick. It could be a tick, or it could be a frame, it could be an iteration. Cycling, like let's say cycling 0 to n minus 1, which is basically I modulo n, cycles through 0, 1, 2 till n minus 1 over and over. So let's contrast division results one more time so it sticks. So 5 divided by 2, which is 2, it's an integer. Integer truncates here. And when it comes to 5 divided by 2.0, it gives you 2.5. Now it's decimal math. 7 modulo 2 gives you 1, which is odd. 16 modulo 5 gives you again 1, since 15 fits. Remainder 1. So expecting decimals from int divided by int, if you need, don't expect that. So if you need a fractional part, convert before you divide. For example, like you could initialize double a and b, and you can divide it, a divided by b, or you could do something like a divided by 2.0. Casting after the division won't bring the fraction back, but it's already gone. So when you're coding, think like, do I need a decimal result? If yes, make one operand and a double, and think, how do I need to check a pattern or schedule? If yes, think modulo. And if you're thinking, am I counting steps or frames and something happens every nth time, that's modulo again. So that's the core idea. So use integer division when you truly want whole number math. Use modulo for reminders, even odd checks, repeating patterns. And when you need decimals, be intentional prompt one operand to double before you divide. Yeah, check these in Zybooks or any IDE and see what happens. Those tiny experiments make the behavior click fast. uh, Type conversions. So let's talk about type conversions, how Java moves values between types. This matters anytime you mix integers and decimals or go from bigger type to a smaller one. So there are two big buckets. First one is widening conversions. So this is where you go from smaller type to larger type, like int to double. Java can do this safely and automatically because you're not losing information. For example, turning 5 into 5.0, that's not a problem. And narrowing, this is when you go from larger type to smaller type, like double to int. Java does not do this automatically because you can lose information. You must explicitly cast it and you accept the risk. Like for example, let's say int and int in brackets 5.9, which becomes 5. The decimal is discarded. So now, why do we care? Because conversions change results, especially in divisions. So if you divide two ints, you get an int. It truncates. If you want a decimal result, you have to prompt the math to use a decimal. The easiest way is to cast before you divide, like double a divided by b. Now Java does decimal division, so you keep the fraction, and if you cast after dividing, like like this, it's too late. The integer division already threw the fraction away, so you just turn 2 into 2.0. Let's make it concrete. Like imagine a is equal to 5, b is equal to 2, and a divided by b, which gives you 2, which is basically int math. And when it comes to like let's say double a divided by b. So here a is 5 and b is 2. This gives 2.5 because a becomes 5.0, so decimal math kicks in. But when you give it like this, so this gives 2.0 because fraction is already lost. It divides first and then it converts into a double. So sometimes you want to cast back. For example, you compute a decimal and then store it as an int for display or indexing. That's fine, but know you're truncating the decimal. If you need rounding, round first and then cast, or format for output instead of changing the values type. So when is caching safe or unsafe? So safe-ish is when is for widening, like into double, no precision lost for the integer part. It's risky for narrowing, like double to int, long to int. You can lose decimals or overflow the range. Using cast as a band-aid when the logic is wrong, that's a big red flag. If your numbers look off, don't slap on a cast to make it compile. Fix the math. Some of the things to remember is silent truncation, which is like int 3.99 silently becomes 3, and casting after the fact. Once int division happens, the fraction is gone. And forgetting ranges, so casting a large long to int can overflow into nonsense. So yeah, so use widening conversions to get decimal math when you need it. Be intentional with narrowing cache. Assume you might lose data. Don't use cache to hide bugs. Use them when the conversion is truly what you want. If you only need decimals for display, consider formatting the output instead of changing the variables type. Yeah, check these in your IDE or Zybugs. Seeing the difference once makes it stick. So the last topic for today is binary. So let's talk about binary, how computers represent numbers under the hood. Don't worry, we are not going deep into bit tricks today. The goal is simple: understand what binary is and how to read write small binary numbers in Java, and also avoid few easy mistakes. So computer stores numbers using bits, zeros and ones. That's binary. Just like we write numbers in like base 10, each position is powers of 10. Binary is base 2, so each position is power of 2. So the binary number 1010 means, let me actually take an example. So 1010, what actually means is 1 multiplied by 8 plus 0 multiplied by 4 plus 1 multiplied by 2 plus 0 multiplied by 1. So this gives us 8 plus 0 plus 2 plus 0, which gives us 10 in decimal. So in Java you can write binary literals directly using the 0b prefix. So like 0b 1010 is the same as decimal 10, and 0b 1111 is 15, which is 8 plus 4 plus 2 plus 1, that's 15. So Java also lets you use underscores for readability in numeric literals. So they don't change the value, they just make long numbers easier to see, like 0b underscore 1010 underscore 1100. It's totally fine, it's still one number. Think of underscores like visual commas. The compiler ignores them. And a couple of tiny conversions to make this real, like binary, let's say 0b11. This is basically decimal 3, which is 2 plus 1. And binary 0b100, which is decimal 4, which is 4 plus 0 plus 0. And 0b1011, which is decimal 11, 8 plus 0 plus 2 plus 1. And another direction is decimal to binary for small numbers, like decimal 6, which gives you binary 110, which is 4 plus 2. Decimal 9 gives us binary 1001, which is basically 8 plus 1. So where this helps you, it helps in reading documents or debugging where flags are shown in binary or hex. So understanding why powers of 2, 2, 4, 8, 16, so on pops up so much. So thinking about ranges. So with n bits, you can represent 2 power n different values. Like for example, 8 bits is 256 values, and which is basically 0 to 255. So some of the things to remember: 0b 1010 is a number, not a string, not a text. If you need text like 1010, that's a string. So misreading underscores 0b1 underscore 000 is just a formatting aid. It's still one number. Don't try to split it on underscores in your head. And yeah, try this in your IDE. Print few literals, convert a couple of small decimals to binary on paper, and then check yourself why printing the decimal and verifying with mental math. Yeah, that's all we need for today. Keep this mental model handy. Binary is just powers of 2. Java's 0b lets you write those values directly. Use underscores to keep long patterns readable, and remember, these are numbers, not strings. That's all for today. We'll cover the rest of the topics from this chapter in the next session. Thank you.